Welcome back to this video series on cryptocurrency. Bloom filters. A Bloom filter is a probabilistic search filter, a way to describe a desired pattern without specifying it exactly. Bloom filters offer an efficient way to express a search pattern while protecting privacy. They are used by SPV nodes to ask their peers for transactions matching a specific pattern without revealing exactly which addresses, keys or transactions they are searching for. In our previous analogy, a tourist without a map is asking for directions for a specific address, 23 Church Street. If she asks strangers for directions to the street, she inadvertently reveals her destination. A Bloom filter is like asking, are there any streets in the neighborhood whose names end in RCH? A question like that reveals slightly less about the desired destination than asking for 23 Church Street. Using this technique, a tourist could specify the desired address in more detail, such as ending in U or CH, or in less detail as ending in H. By verifying the precision of the search, the tourist reveals more or less information at the expense of getting more or less specific results. If she asks a less specific pattern, she gets a lot more possible addresses and better privacy, but many of the results are irrelevant. If she asks for a specific pattern, she gets fewer results but loses privacy. Bloom filters serve this function by allowing an SPV node to specify a search pattern for transactions that can be tuned towards precision or privacy. A more specific Bloom filter will produce accurate results, but at the expense of revealing what patterns the SPV node is interested in, thus revealing the addresses owned by the user's wallet. A less specific Bloom filter will produce more data about more transactions, many irrelevant to the node, but will allow the node to maintain better privacy. How Bloom filters work. Bloom filters are implemented as a variable size array of n binary digits, a bit field, and a variable number of mhash functions. The hash functions are designed to always produce an output that is between 1 and n, corresponding to the array of binary digits. The hash functions are generated deterministically so that any node implementing a Bloom filter will always use the same hash functions and get the same results for a specific input. By choosing the different length n Bloom filters and the different number m of hash functions, the Bloom filter can be tuned varying the level of accuracy and therefore privacy. Figure 8.8, we use a very small array of 16 bits and set of 3 hash functions to demonstrate how Bloom filters work. The Bloom filter is initialized so that the array of bits is all zeros. To add a pattern to the Bloom filter, the pattern is hashed by each hash function in turn. Applying the first hash function to the input results in a number between 1 and n. The corresponding bit in the array indexed from 1 to n is found and set to 1, thereby recording the output of the hash function. The next hash function is used to set another bit, and so on. Once all M hash functions have been applied, the search pattern will be recorded in the Bloom filter as M bits that have been changed from 0 to 1. Figure 8.9 is an example of adding a pattern A to the simple Bloom filter as shown in figure 8.8. Adding a second pattern is as simple as repeating this process. The pattern is hashed by each hash function in turn, and the result is recorded by setting the bits to 1. Note that as a Bloom filter is filled with more patterns, a hash function result might coincide with a bit that is already set to 1, in which case the bit is not changed. In essence, as more patterns record on overlapping bits, the Bloom filter starts to become saturated with more bits set to 1, and the accuracy of the filter decreases. This is why the filter is a probabilistic data structure. It gets less accurate as more patterns are added. The accuracy depends on the number of patterns added versus the size of the bit array n and the number of hash functions n. A larger bit array and more hash functions can record more patterns with higher accuracy. A smaller bit array or fewer hash functions will record fewer patterns and produce less accuracy. Figure 8.9, adding a pattern A to our simple Bloom filter. Figure 8.10 is an example of adding a second pattern B to the simple Bloom filter. To test if a pattern is part of a Bloom filter, the pattern is hashed by each hash function, and the resulting bit pattern is tested against the bit array. If all the bits indexed by the hash functions are set to 1, then the pattern is probably recorded in the Bloom filter, because the bits may be set because of the overlap from multiple patterns. The answer is not certain, but it is rather probabilistic. In simple terms, a Bloom filter positive match is maybe yes. Figure 8.11 is an example of testing the existence of pattern X in the simple Bloom filter. The corresponding bits are set to 1, so the pattern is probably a match. On the contrary, if a pattern tested against a Bloom filter and any of the bits is set to 0, this proves that the pattern was not recorded in the Bloom filter. A negative result is not a probability, it is a certainty. In simple terms, a negative match on a Bloom filter is a definitely not. Figure 8.12 is an example of testing the existing pattern Y in the simple Bloom filter. One of the corresponding bits is set to 0, so the pattern is definitely not a match. Figure 8.12, testing the existence of pattern Y in the Bloom filter. The result is a definite negative match, meaning definitely not. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.